In this video, we'll check out the energy model with work. Work is a transfer of energy into or out of a system. When it's into the system, it's positive, and when it's out of the system, it's negative. Let's review the energy model with an example. Let's check out this PhET simulation. Let's check out this simulation of the skateboarder going up and down this ramp. The blue pie chart right above him represents the total amount of energy. The blue represents potential energy, and the green that you're about to see represents the kinetic energy. So I'm going to press the start button, and we'll see what happens to that total amount of energy. Notice that that energy goes from being blue to green. Again, blue is potential energy, and green is kinetic energy. Let's slow him down. Now, again, when he gets to the very, very top, it gets all blue. Then when he gets to the very, very bottom, it turns all green. It's blue at the very, very top, all blue at the very top, because he's got all potential energy, gravitational potential energy that is, and at the bottom, all green, because at that point, he's got all kinetic energy and no potential energy. Notice that the total amount of energy never changes. In other words, if you look at the pie chart stays exactly the same. It doesn't get any bigger, doesn't get any smaller. It just goes from being green to blue, or some combination in between. Okay, well, let's check out the bar graphs for that simulation that we just watched. When the skateboarder was at the very, very top, we'll notice that all the energy is gravitational potential energy. Remember, this situation has no friction. When the skateboarder is somewhere in the middle, he's got some kinetic energy and some gravitational potential energy. Obviously, no spring potential energy because there's no spring involved. Then when he gets to the very bottom, he's got all kinetic energy and no gravitational potential energy. When he gets towards the middle of the other side of the ramp, then he's got some kinetic energy and some gravitational potential energy. And then when he gets to the top of the other side of the ramp, then it becomes all gravitational potential energy. This happens only because we're saying there's no friction. Notice that the total amount of energy doesn't change. There's no friction, and our system includes the skateboarder and the earth. So if we call the beginning situation this setup right here, he's got all gravitational potential energy. At the end, which we'll call that situation there, just arbitrarily, has both kinetic energy because he's moving and gravitational potential energy because he's above ground level. So what we can say is at the beginning, he's got all gravitational potential energy. At the end, because he's got some kinetic energy and some gravitational potential energy, and the size of these pie charts don't get any bigger or any smaller, they remain constant, we can say that all of the gravitational potential energy at the beginning turns into a combination of the kinetic energy and gravitational potential energy at the end. Now, we have to ask ourselves a question: is energy transferred into or out of the system? And our answer is no. The reason the answer is no is that the total amount of energy at the beginning is equal to the total amount of energy at the end. So therefore, there's no transfer of energy. No work is done. Let's check out the same example, but this time, let's introduce some friction. Now, let's check out what happens to our skateboarder when we introduce friction. So he's going to start from the same position as before. I'm going to hit the start button, and we'll see what happens to him. Oh, notice what happens to the size of the pie chart. Let's watch them all slow all the way down. Notice that the pie chart basically goes to 0. This time, let's watch him in slow motion. This time, let's look at what happens to the skateboarder on the ramp if we introduce friction. Our system is still the skateboarder and the earth. At the very beginning, the skateboarder still got all gravitational potential energy, let's say 4 units of gravitational potential energy, and there's the size of its pie chart. It's all blue because it's all gravitational potential energy. When he gets to the bottom, it turns all green because now it's all kinetic energy. However, notice instead of having 4 units of kinetic energy, we've only got 3 units of kinetic energy because we've lost 1 kinetic energy due to friction. It's turned into thermal energy or heat. As he continues up the other side, notice the size of the pie chart continues to diminish, again because of friction, and now it's all the gravitational potential energy is just 2 units of gravitational potential energy. When he gets back to the bottom, the pie chart's even smaller. He's got nothing but kinetic energy, but it's a lot less. There's only 1 unit of kinetic energy left. Then he gets up to the other side with just a little bit of gravitational potential energy. And then at the very end, he's got no energy because it's all dissipated due to friction. So at the very, very beginning, the skateboarder, our system, which is a skateboarder in the earth, had nothing but gravitational potential energy, 4 units of it. At the end, there's no energy, no kinetic, no gravitational potential, and no spring or elastic energy. So what happened to this energy? We know at the beginning, there's all gravitational potential energy. So what we therefore say is that all the energy that we had at the beginning transferred out of our system. So what we do is we draw a big old arrow showing that the energy is being transferred out of our system due to work. So we went from having 4 units of gravitational potential energy to having 0 units of gravitational potential energy. We have to ask ourselves, what did the work? In this case, friction did the work. How did it do the work? It transferred energy out of the system, and that's considered negative energy. A negative transfer of energy. So our gravitational potential energy therefore became, or our gravitational potential energy transferred out of the system because of work. And we use F sub k to denote that it's kinetic friction that did the work. All right, so this is our complete model of the energy model with work. Our system includes all the objects that can influence the energy of our system, the kinetic energy or the potential energy. The total amount of that total energy of our system is called the mechanical energy when we add up all the kinetic and all the potential energy. Now, work can be done to our system. We consider that positive work, or work can be taken out of our system or transferred out of our system, which is considered negative work. Let's always use these steps in our energy model. Drawing a picture, drawing a bar graph, and defining the system, making an energy statement and including conservation, writing the energy equations, and solving for our unknowns. Now, work is a transfer of energy, either into or out of the system. To understand work, we need to understand what we mean by our system. Our system includes all the objects that have the ability to influence the energy of the system. It's important to be able to define that system. In other words, we must state which objects are part of the system. Then we have to determine what is transferring the energy and how it's transferring it. Now, there are 4 examples that I list here. For example, gravity from an object like a planet outside of our system can exert a gravitational force on an object inside our system, thereby making it move and giving it kinetic energy. In a similar way, a force by an object like a person outside our system can exert an applied force on an object inside our system, thereby making it move and giving it kinetic energy. This is called mechanical work. Another example would include a spring outside of our system exerting an elastic or spring force on an object inside our system, thereby making it move and, once again, giving it kinetic energy. Or an object with kinetic energy inside our system experiences frictional forces on it that transfer thermal heat out of our system. All right, now we talked about mechanical work. For mechanical work, only the component of the force in the direction of the displacement matters. So notice this force is at an angle. This object is going to move this distance that we call r in this equation. If there is some angle theta, only the component of the force in the direction of r matters. So only this direction of the force matters when it comes to determining the work in this particular system. So let's say the cart above moves 10 meters, that would be our R, when a person applies a 15 Newton force at 37 degrees. How much work is done on the cart? Well, again, what we want to do is we want to look at just the horizontal component, or the component of the force in the direction of the displacement. So we would use this equation. We would plug 50 newtons into our force. The distance that we're going to move it is 10 meters. So that's why we plug 10 meters there. And our angle is 37 degrees. So again, the important thing here for mechanical work is that only the component of the force in the direction of the displacement matters. So if all of the force is pointing in the same direction, then this equation simply becomes F times D. Now, the work energy theorem states that any change in the kinetic energy of a system is due to work done to or by the system. On the AP test, you're expected to know this. However, the work energy theorem comes out as a result of the energy model. So while it's important to know the work energy theorem, we should know that our energy model proves the work energy theorem. Let's see what would happen to a bulldog riding a roller coaster on the moon. Oh no!